CIRCE is a research center. We are based in Zaragoza in Spain. I personally am part of the recycling technologies team, where we work on developing recycling technologies, as the name indicates, for different kinds of wastes. We work with, construction demolition waste, plastics, textiles, electronic waste. We do a range of them. And our work is to find innovative technologies. We mostly use microwaves, and we try to use green solvents and to reduce the impact of our processes. And within the framework of STREP, we are focusing our work on the development of a technology for recycling cotton using hydrothermal liquefaction, which is a process of high temperature and pressure. And the objective is to break the cotton and obtain bio-oils and biochars. So I think it might be interesting that we start by defining what green actually means, just for a second. So at least in the context of recycling, and particularly in the context of STREP, I think it's important. So the term green refers to a process that is measurably better for the environment when you look at the whole system, not just one step. So basically, it's like the full picture, not just one of the stages, and it entails like lower overall impacts across the life cycle, such as reduced greenhouse gas emissions and energy demands, lower water use and pollution, and also the careful control of any unintended releases, like, for instance, wastewater contaminants or dust or microfibers or microplastics, for instance. Honestly, those unintended releases are often where the real issue hides. So it's where you need to pay attention. This term also implies that a safer and more responsible use of the chemicals and materials, ideally minimizing the hazardous substances or keeping them in closed loops, so you recover them and you avoid the release of the substances. And I think that finally, like, a truly green process creates a real circular value. So it produces outputs that reliably replace the virgin or the fossil-based products, and with relatively or very good yields, and also limited secondary waste. And another very important thing is that it should be, you should be able to scale it without the footprint increasing. So if you do it at small scale and it's good, it should be equally good at larger scale. So if I have to say the term green defines something, is this. So a recycling process is only truly green if it delivers like a net environmental benefit when you look at the whole system, and not just the fact that it's recycling for the sake of it. And I think that's really the main point. It has to be measured with life cycle thinking. So how much energy and water are you using? What emissions are you generating? How much waste are you avoiding? And one thing that is very important, whether the recycled outputs actually replace something that would otherwise be made from virgin material. So, I mean, you have to consider this, because if it doesn't replace anything, you are not actually gaining much, you are adding. So I think that's very important. And yes, recycling can sometimes be worse than actually not doing anything. It's not the answer people expect, I assume, but it's actually true. Because if a process uses a lot of energy, for instance, or it relies on hard to manage chemicals, or produces an output that doesn't really substitute any conventional product, so then you will have a footprint that can be higher than actually producing something new. So recycling isn't automatically a green option. It depends on the process and on what you really want to get out of it. So for example, if we look at the particular case of the synthetic textiles, like plastic or PET textiles, you will have microplastics pollution. That's a real concern in these processes, because the fibers are released when you use them, when you wash them, when you crush them, when you mechanically stress the fibers. So when you cut them, you will likely have release of microfibers, and microfibers are microplastics. So you can see how it becomes like a system issue. So some studies have even shown that recycled PET can shed more during washing, depending on how it's made. So you have a real problem there when you're treating the material. And I think that's why you need to assess the life cycle metrics and to look at any unintended emissions so you can divert the waste. Because diverting the waste and recycling doesn't always mean that you're going after the better option. And I think that's why STREP is what we're focusing on the project, because we're allocating the right textile waste to the right recycling route. We are not just recycling for the sake of it, and we validate the performance with sustainability metrics, and we don't make any assumptions. So I think we're trying to be very practical and evidence-based about it. So we are, as I mentioned earlier, we're focusing on recycling waste cotton textiles using HTL, so hydrothermal liquefaction. Here what we do is we prepare the cotton by cutting and drying it, and then we process it at really high temperature and pressure. And we use water as the medium, and we use an inert atmosphere. So we also test and control the range of temperatures, the residence times, and the agitation conditions of the reactor. And we're testing everything in a very controlled way. And our goal is to optimize the HTL operating conditions so that we can have consistent production of the high quality bio-oils and biochars that I was mentioning before. So at lab scale, our goal is to turn a process that works into something that is repeatable and controllable, because that's what you actually need for being able to scale it up. Because scaling is where the inconsistencies can get really expensive if you are not managing them. So as mentioned, we are currently operating at lab scale, which is where we lock down the repeatability. So we develop the recipe, the mixing, the whole process, and we have a robust product recovery. So we are trying to make the whole thing as reliable as possible. And for this, you need to look at the reaction severity, for instance, so the temperature and the residence time, because they control the balance between producing oils, biochars, and the gas. So it will depend on the conditions, how much you get of each of them. So we are tuning all the conditions so that we can balance the results, and watching how changing each one of them actually affects the results. The other thing that we have is the mixing and the heat transfer. So agitation also matters a lot in this kind of processes, and scale up often fails in mixing. And sometimes this is a variable that is not well understood. So we need to be very thorough on that. And that's something that we are working and trying to optimize at the moment. And then third, we are standardizing the product separation and analytics, because you treat the cotton, you get the product, but everything is mixed. Not the gas, of course, but the bio-oils and the biochars are mixed, so you need to separate them. And we are working on that, and also trying to calculate the mass balances and compare which are the conditions that are better. And we do that by analyzing the oils and the char composition. So for the oils, we do a composition analysis, and for the char, we do a structure and elemental composition analysis. And that way, we have data that is solid for each of the runs. So we can finally link the operating conditions to the product qualities. Because, I mean, at the end point is not just to make oil and char, but it's actually to make good and consistent products that are actually suitable for real applications. So we are already seeing promising results with the oil and the char characteristics, and this phase is just about mapping the conditions that produce them reliably. So that when you go bigger, you actually know what you're aiming for, and you can be certain that your process is going to give you the results that you're expecting, and the products that you are expecting that will be actually useful in larger scale processes. We are So mechanical recycling works best when the cotton is relatively clean and the fibers are still long and strong enough to be respun. So when the feedstock is good, it's really a strong option to go for mechanical. But in real waste streams, let's say, cotton often arrives already tired. So the fibers are shortened by wear, they are blended or heavily finished or contaminated in ways that make the fiber to fiber recycling difficult and the output lower quality. And I think that's the challenge with real world textiles, the quality of the materials when they arrive to the recycling processes. So the biggest technical advantage of HTL is that it doesn't need to protect the fiber integrity at all because we are actually destroying it. So it's not dependent on keeping fibers long or keep them spinnable. So instead of trying to rebuild a textile fiber from a degraded fiber, HTL reveals the value of the cotton at a molecular level. And it converts the cellulose-rich cotton into a bio-oil and biochar that can be tailored through the process conditions. So what we're actually doing is creating value in a different way. And I believe that what that brings to the table is flexibility and control, and that's a big advantage. So with HTL, we can tune the temperature, the time, the agitation, as I was mentioning before, so that we can steer the process towards either more oils or more solids, and to match those properties to the application that we want. So it's not like a single output, it's something you can steer depending on what you're after. So for example, biochar can potentially be developed as an absorbent material, a functional filler in polymers or in building materials, or a carbon material or a support for other applications. And on the other hand, you have bio-oils that can be explored as a renewable feedstock for fuels or a chemical fraction depending on its composition. So there are multiple variable routes that you can take depending on the products that you select with your conditions. So I think in other words, what I'm trying to say is that HTL doesn't just recycle the cotton, it creates a platform road for the cotton fraction that mechanical recycling actually struggles with. So it fills a real gap, it's complementary, it's not in competition with mechanical recycling, it complements it. And importantly, it fits the step logic of the right flow for the right stream. Mechanical recycling remains to be the best option when the textile quality allows the fiber recovery, but HTL provides an alternative pathway for the cotton fraction that would otherwise be downcycled or even discarded. And it helps increase the overall recovery and value from the textile system. So it's really about complementing the mechanical recycling, as I was saying, and not replacing it. So